Okay, now let's solve a differential equation using Frobenius series. As an example, we'll solve this problem. 2x y double prime minus y prime plus 2y equals 0. If you put it in standard form, you would divide through by 2x, or p would be minus 1 over 2x, or q would be 1 over x. The roots of both denominators would be both 0 and not repeated. So 0 is a regular singular point, which means we're guaranteed at least one Frobenius series solution. There's no other singular points, so the radius of convergence is infinity. So the interval of convergence will be 0 to positive infinity. We go about it much like with power series. Only now we have a Frobenius series. Here is the Frobenius series. Here's its first derivative. Here's its second derivative. First thing we do is simply substitute in those terms for the y prime, and y double prime. It's just this line here. Then we proceed pretty much like we did power series. We can bring in what's outside the sum inside the sum. And I'm also going to bring out x to the r, because each of these has an x to the r power in it. So I'll bring out x to the r and bring in what's outside, otherwise outside. So this guy will be 2, and then I'll raise this guy's power by 1. So it'll be n minus 1. Pull the r out. These guys stay the same. I can bring this 2 in. And now, because it all equals 0, what's in brackets here equals 0. And I can get rid of this, quit thinking about this x to the r term for now. Once we put the solution together, we have to remember to bring it back in. So this, what's in brackets here, is going to equal 0. So that's where we're left. Now we do it like power series, see where each, what power of x each sum starts at, because we want to start them all at the same power. This guy starts at x to the minus 1. This guy starts at x to the minus 1. And this guy starts at x to the 0. So to get them all to start at the same one, we want them all to start at x to the 0 in this case. We'll pull off this guy's first term and this sum's first term. So we'll pull them out. We'll have a 2 c sub 0 r times r minus 1 x to the minus 1. This guy's first term, c sub 0 r x to the minus 1. Then we start these two sums at one index higher, because we just pulled off the first terms. So this guy now starts at n equals 1. This guy now starts at n equals 1. Next step is just like with power series. Switch the indices, and I do it by setting k to my exponent. So this guy's k will be n minus 1. Same here, and this guy will just be n. These two upfront terms both have a c sub 0 in common and x to the minus 1 in common. So we pull them out. Here's what's left after we switch indices. We can check it again. Do they all start at the same k? They all have the same powers of x? Yes. If that's not true, you did something wrong somewhere. And this simplifies a little bit. It's r times 2r minus 3. And when I put all these three together, it simplifies a little bit algebraically. And at this point, we employ the identity property again. Every coefficient of every power of x must be 0 for the whole sum to be 0. So this term must be 0. And what's in brackets here must be 0 for every k from 0 and up. For this term to be 0, I could say C0 equals 0. But that never happens with a Frobenius series. that first coefficient, the C sub 0 coefficient, is never 0 in a Frobenius series. We're going to set it to 1, but we can't set it to 0, which means this other part must be 0, which gives us a quadratic equation. And it has two roots. R can be 3/2 or 0. We call the larger one R sub 1. Larger meaning further to the right on the real line. And the smaller one, R sub 2. These guys are called the indicial roots. And this other term will give us a recursive relationship. So yeah, this quadratic equation yields the indicial roots. And R1 is always greater than or equal to R2 by the way we define it. This will become more important in the future. And then we have this recursive relationship. We have two different R's. So we go through the process for each different R. For the larger indicial root, that's when R equals 3/2. Plug it in here, and it's algebraically simplifies a little bit so we can use all whole numbers. That gives us a recursive relationship. I won't go through the arithmetic. Here's the first 3 terms after C sub 0. And we could put this together like we do a power series. So we have the C sub 0 term, C sub 1 term, etc. Here's something, don't get sloppy and forget. The Frobenius series has this x to the r term in front of it, or this extra power of x. In this case, r equals 3/2. So we have to multiply this parenthetical part by x to the 3/2. And that gives us our first particular solution. Then we can try it with the other indicial root, and that was 0, which gives us this recursive relationship. Calculate the first 3 terms again. And in this case, x to the r is x to the 0, which is just 1. So this second particular solution is a Frobenius series that happens to be a power series. Again, C sub 0 is 1. And in this case, C sub 1 is 2, C sub 2 is -2, etc. There's the second particular solution. General solution would then be a linear combination of these two particular solutions. I'll just say we're not always guaranteed to find 2 series solutions that are our particular solutions. I'm getting ahead of myself a little bit here, but you're always guaranteed to find a Frobenius series solution for the larger indicial root. But you're not always guaranteed to find a second series solution. If you do, it will be based on the smaller indicial root. And we'll leave that for future discussion.